Alrighty, howdy folks. Section 3 of chapter 15, and this is about doing double integrals in polar coordinates. A pretty interesting thing and a pretty useful thing that especially if you are engineering or physics major, you will bump into this quite a bit. Using polar coordinates. I think I mentioned before that anytime you have some kind of a radial symmetry, meaning something that looks kind of circular in cross section or a part of a circle, in those situations you are better off using polar coordinates, formulating your equations in terms of polar as opposed to Cartesian coordinates. Okay. And take, for instance, an equation of a circle. We are looking at this region that is covered by the circle x squared plus y squared equals 1. So the interior part of the circle is what our region is. So basically, what's the idea here? Since we are looking at double integrals, we want double integral over this domain of some f of xy dA. That's the whole idea. What's that? Integral over this domain D, double integral over this domain D of some function f of x and y dA. So the domain is this one. Now look at this. Y polar. The equation of a circle in Cartesian is what? For example, this circle is x squared plus y squared equals 1. That means its center is located at 0, 0, and it has a radius of 1 unit, right? Do you know what the equation of this circle is in polar coordinates? It's a pretty complicated one. The equation is r equals 1. That's it. That's a joke, man. That's it. Can you imagine, instead of saying x squared plus y squared equals 1, you just say r equals 1. That's it. It's a circle with center 0, 0. Center is what's called a polar axis and radius of 1. The idea there being, theta can be anything, is what you're saying. Theta can be 0 radian, 0.001 radian, 0.002 radian. Each time the radius is going to be 1. Well, that is nothing but a circle, right? No matter what the angle is, you need to go from the polar axis a distance of 1 unit. That's nothing but a circle, right? That's the advantage. So, okay. And so how do we write this? When we look at this, we say D, in this case, is a set of ordered pairs R theta, where R lies between 0 and 1, and theta lies between 0 and 2 pi. That's because this is a full circle. Now, on the other hand, if we have something of this kind, so the domain is the annulus, meaning something that's between two circles, in this case two semicircles. Okay, the outer circle is governed by the equation x squared plus y squared equals 4, which means the radius happens to be 2, and the center of that circle is located at the origin, and the inner circle has a radius of 1. How do we write that? Well, that's D. That D is a set of all points r theta, such that r lies between 1 and 2 and theta lies between 0 and pi. Why it is pi? Oh, that's because it's only a semicircle, right? Half of a circle. And clearly, this is theta equal to 0, and that angle is theta equals pi. All right? Okay. Recall that the transformation, how do we go from polar to Cartesian? Well, that's clearly given by r squared equals x squared plus y squared. and x equals r cosine theta, y equals r sine theta, and tangent theta is y over x, right? So that's something that you need to recall and keep in mind. Okay. Now check this. This is very crucial. In this figure, what we are seeing is the part A says, what if your domain is this annulus, this region that is governed by two sectors of a circle. Okay, a sector is what? A part of a circle. So there's an outer sector and an inner sector. And the outer sector is given by, it starts at theta equals alpha and ends at theta equals beta, both of them. Theta equals alpha and theta equals beta. And the inner circle has a radius of A, and the outer circle has a radius of B. Okay, so that seems to be, that is our region. And how do we go about integrating over this region? Well, just like we took area and split it into rectangles, we will do precisely the same. We will split this into rectangles, but these rectangles are not like the Cartesian rectangles. These are called polar rectangles, itty-bitty polar rectangles, right? Now, if we were to take, just to zoom in and take a little piece of this and look at that, that's going to look like this. Okay, now let's focus on this and try to understand exactly what we are talking about. Just as we have dx and dy, we have delta theta and delta r. What is delta theta? The change in theta. So for example, this particular line has a certain theta, and this other line has a different theta. So what is the change in that angle? That is delta theta. And that is magnified here. So we have that particular line, and that has some angle, and then the angle is different here for this line, and so the change in that angle is delta theta. Okay, this portion corresponds to that inside ED part, and that outside corresponds to this outside one. Okay, now what's the radius of this one? Well, that means that's actually the radius from here to here, radius to this point, right? So that is equal to some r value, and then we have a change in the radius, so that is the delta r. Are you clear about this one? So delta theta is the change in the angle, and delta r is the change in the radius of this itty-bitty differential element. And the key here is, please absolutely pay attention to this one. This is the biggest thing. What is the area of this polar rectangle? Well, in case of a regular one, dx and dy, or delta x and delta y, are the dimensions. So we say, oh, that's nothing but delta x times delta y. Well, if that is the case, is this delta r times delta theta? Ah, no. You would be wrong if you were to say it is delta r times delta theta. That's why I'm saying to pay attention. And that is because the delta r part is okay. There's nothing wrong with the delta r. But is it really delta theta? Delta theta is just an angle, a change in the angle. So what we want is actually the arc length. Are you with me? You want the arc length. And of course, there is a question here. When we say arc length, should we take the inside arc length, or the outside arc length, or some other point? Well, in in this case, let's do this. Let's take the midpoint and say, whatever is the radius from here to that midpoint, and when it comes to the arc length, we will say the arc length at that point. So we draw an arc here. What's the length of that arc? If you recall, length of an arc is equal to radius times theta. Length of an arc is the radius times the angle subtended by that arc. So if we draw an arc here, that delta theta, that is the angle subtended, delta theta, and radius is this rij. So rij times delta theta gives us the arc length, and now multiply that by delta r, we got the delta a. That is the key. Now we can say this in terms of delta r and delta theta, or we can say in terms of dr and d theta. So we will say dA is equal to r dr d theta. That's the key. So it shows this region, which is a set of all points r theta, such that r lies between a and b and theta lies between alpha and beta. Okay, so we pick this one. And like I said, we can say delta theta or d theta. R d theta is going to be this arc length, and dr is the change in radius, dr, delta r dr. So dA is nothing but the arc length r d theta times dr, r dr d theta. Cool. What else? Yeah, that's the main thing. So wherever we have dA, be absolutely sure to say r dr d theta, not just dr d theta. Cool. Let me remind you, in Cartesian, you will replace dA with a dx dy, dx times dy, whereas in polar, you replace dA with r dr d theta. And I'll show you quite a few problems. Okay, what else? Yeah, change to polar coordinates in a double integral. Yeah, okay, cool. If f is continuous on a polar rectangle D, polar rectangle, you remember that one that I showed in the previous figure? This guy, A. So that's what we are talking about here. If f is continuous on a polar rectangle D given by 0 less than or equal to a, less than or equal to r, less than or equal to b. Whoa, wait a minute. What's with this? 0 less than or equal to a less. I thought a less than or equal to r, less than or equal to b. What's up with 0 less than or equal to a? That is because they are telling us that the inner radius cannot be less than 0. Inner radius A has to be greater than or equal to 0. Equal to 0 is fine, but cannot be less than. That kind of makes sense, right? Radius cannot be negative. In this context, there is a situation where in polar coordinates there is a concept called r equals -1 or some negative value. It has some meaningful significance in polar, but in this case we are clearly establishing that r has to be greater than or equal to 0. Okay, the inner radius has to be greater than or equal to 0, and outer radius is less than or equal to b. Okay, and in fact the outer radius b must be bigger than the inner radius. You don't want that common sense, right? Inner radius means that has to have a smaller value of radius than the outer one. Okay, what else? Excuse me. And theta should lie between alpha and beta, and in such a way that you cannot just that's interesting, right? Can we pick any values for theta? As long as alpha, can we pick any angle for alpha and beta? as long as the alpha is less than or equal to beta. This is saying, no, you cannot do that. You must pick alpha and beta in such a way that beta minus alpha has to be between 0 and 2 pi. Okay, that means we cannot talk about, say, a circle that is traversed more than once. What's the implication of making this beta minus alpha less than or equal to 2 pi? That is to say that you cannot traverse a circle more than twice. The polar form may allow us to do that, but so far as these regions are concerned, that's a no-no. At most, the difference between the, how should we put it, the starting angle at the ending angle and the initial angle, at most has to be 2 pi. Okay, and must be greater than or equal to 0 at the same time. In that case, if our objective is to evaluate f of xy dA over this region D, then the outer integral alpha to beta is with respect to theta. That part is similar. And inside would be a to b. That is r equals a to r equals b. And x is r cosine theta, y is r sine theta. That's what we did. We replaced the polar form of x and y, r cosine theta and r sine theta. And now here is that big one. dA, what do we replace dA by? Certainly, like I was mentioning, do not replace dA by just dr d theta. You must say r dr d theta. That's exactly what's happening here. Cool? All right. Over a general, oh, okay, this is interesting. What about a general polar region? That was a nice polar rectangle. Well, there's a situation here where we have the starting angle theta is alpha and the ending final angle is theta equals beta. But this is not between two constant radii, r equals a and r equals b, and instead we have functions that govern this radius, inner radius and the outer radius, functions of theta especially, right? R is equal to h1 of theta to r equals h2 of theta. Okay, can you imagine what it is that we need to do in a situation like this? So I'm about to show you, but I want you to kind of take a guess. So integral d and double integral d over d of f of xy dA, what would change here? Would f of r cosine theta, r sine theta, will that be the same? Yep, that's going to be the same. And dA, should we replace that with r dr d theta? Yep, that's going to be the same. Cool. This limits alpha to beta, which are the limits on theta. Theta equals alpha to theta equals beta. Is that what we would do? Yep, theta equals alpha, theta equals beta. So that doesn't change. Cool. What about a to b? R equals a to r equals b? Obviously, that's the one that's going to change. Instead of saying integral a to b, we'll say h1 of theta to h2 of theta. That's the only difference. Cool. If it's and all these things, you know, continuity has to be there. Continuity has to exist for us to talk about integrals. Okay. So like I said, this is how we will handle general polar regions. Cool. All right. Now, sketch the region whose area is given by the integral and evaluate the integral. What? Sketch the region whose area is given by the integral and evaluate the integral. What does that mean? Pi over 2 to pi. What are the limits on? Obviously, the outer one, right? So theta. Oh, this is saying theta equals pi half to theta equals pi. All right. What about 0 to 2 sine theta? 0 to 2 sine theta is r equals 0 to r equals 2 sine theta. Cool. So theta limits are fairly clear. Theta equals pi half to theta pi. So that's like the 90 degrees to 180 degrees. Yeah, we can clearly imagine that sector, right? But the question is, oh, and r equals 0 also, we know what it is. But what's up with r equals 2 sine theta? That is the one that will pose a little bit of complexity. All right, folks. So this is the one that requires a bit of thinking. And perhaps in our case, I'm okay with using Geogebra for it. But at the same time, you really have to try to figure out these kind of things. So I'm going to show you a few things, the straightforward mathematical way, and then the Geogebra version of it also. Okay, what are we trying to show? What in the world is this r equals 2 sine theta, right? Okay. When r is 2 sine theta, would you agree that I can multiply both sides by r and say r times r equals 2r times sine theta, r times 2 sine theta? So that gave me r square equals 2r sine theta. Okay, why did I do that? I did that because if we look at the polar to Cartesian form, r square is nothing but x square plus y square. Right, r equals x cosine theta, x equals r cosine theta, y equals r sine theta. So if we multiply, if we say x square plus y square, that is r square cosine square theta plus r square sine square theta, but we can factor out an r square, all that stuff. So r square is nothing but x square plus y square. And r sine theta is y. So the polar version of this, the Cartesian version of this polar equation, r equals 2 sine theta, is x square plus y square equals 2y. Why did we do this? Why did we go from polar to Cartesian? Because the polar part didn't give us an idea of what exactly that polar curve would look like. So we are wondering, hey, if we change it into Cartesian, would we have a sense of what that curve should look like? That's what we are doing. Well, the big question now is, do we have any idea what x square plus y square equals 2y, that curve looks like? Yeah. Can we do this? Right. If you recall, we did these kinds of things in the very beginning of the semester. I gave you some equations and you needed to, of a circle or a sphere, and you needed to figure out exactly what the center of the sphere was and what the radius of the sphere was, right? Here we are talking about a circle. What is this an equation of? Well, you do a completing the square part, so that the whole idea is we want to write this as x minus h the quantity square plus y minus k the quantity square equals sum r square. Hk would be the center and r would be the radius. So that's exactly what I'm doing. To complete the square and y square minus 2y, I'm adding a half of this. Half of the coefficient of y is -1. I'm adding a -1 the quantity square. Okay, -1, the quantity square is just +1, so I'm adding a 1. And to compensate for adding a 1 on the left hand side, I'm adding a 1 on the right hand side. And what that did is made this into a perfect square. That's exactly what the purpose of completing the square is, so that you can get a perfect square here. And so x squared plus y minus 1, the quantity square, is equal to 1. So what is this now? Well, this is a circle whose center is 0, 1. X minus h, the quantity square, h is 0, plus y minus k, the quantity square, k is 1. So 0, 1 is the center, is equal to r square. 1 square is 1. So r is 1. So this is basically a circle whose center is located at 0, 1, x equals 0, y equals 1, and it has a radius of 1 unit. That's what it is. Did I say circle? Then how come I'm showing a semicircle? Oh, that is because we have r equals pi half to pi. Theta is equal to pi half to pi. So theta equals pi half is this line, and theta equals pi is this line. So we just take that. All right. So much of thinking needs to go into figuring out these polar curves. The Geogebra way is another way of figuring this out. And since pi half, okay, an alternative figuring out the region is to go to Geogebra and type these commands in sequence. So what exactly are we trying to do? We're trying to find what this 2 sine theta is. R equals 2 sine theta, what it looks like, and with the theta going from pi half to pi half. All right. So first, because we want 2 sine theta, let's just say f of x equals 2 times sine x. The idea here is, you don't want to keep typing f of thetas many times. So you just say f of x equals 2 sine x. As soon as you type this, it will show you a graph of a sine curve. Okay. You can turn the visibility off for that function. You just click on that dot and you can turn that visibility off. You need the f of x, but you don't need to see the curve that it represents. Okay. What do I mean? Let me show you. And the next command that you type is curve f of t times cosine t, comma, f of t times sine t, comma t, comma pi over 2, comma pi. What in the world is all of this? Well, this is a way to draw a parametric curve. The parameter here is t, and x as a function of t, y as a function of t. The parameter itself, you need to state what the parameter is, and that's the t here. Okay, and the next is, what is the value, what's the range of that parameter? Well, t, here the parameter goes from pi half to pi. Those are the three things. X of t, y of t, the t itself to indicate that's the parameter. Lower limit of the t, upper limit of the t. Cool? Now, how come this x of t is f of t times cosine t? Well, isn't x equal to r cosine theta? Polar coordinate. X equals r cosine theta. But r is equal to 2 sine theta here. That's why we made it as some f of x as 2 sine x. Had this been, let's say, 2 cosine square theta, well, we would have said 2 times cosine of x times cosine of x. Right? 2 cosine square x is what we would have said f of x. And GeoGebra has the smarts built in where after you say f of x equals 2 sine x and you say here f of t, it automatically knows, you mean 2 sine t. Yep, that's what we want. So we say 2 sine t times cosine t to indicate r of t, r times cosine or cosine theta to stand for x. Cool. X equals r cosine theta. R itself is 2 sine theta. So that's what we are saying. And similarly, y is r sine theta. So r is given by 2 sine t based on this, 2 sine theta. So 2 sine theta times 2 sine theta times sine theta, right? R times. Now, I'll be honest with you. You didn't have to do this f of x way. You could have said, I don't care, man, r is 2 sine theta, so I'm going to say 2 times the sine of t times cosine t. You could do that. But be sure to say the same thing for r here, 2 times sine t times the sine of t. Okay? If you did that, then perfectly fine. And like I said, this t is just to indicate that that is the parameter, and we are giving the lower and higher values of the parameter. So if you do that, you will see a polar curve. And what we did here is, since we wanted to plot a polar curve, 2 sine theta, we took the Cartesian form x equals r cosine theta, where r is replaced by f of theta, and y equals r sine theta, and r is replaced by f of theta sine theta. And when you do that, you will actually see this polar curve. Cool? It'll show you this. And so, folks, all that amount of work had to go through, we had to go through for this. So these could be just a tad tedious. But I hope things were clear. Okay, what else? Yeah, we saw this and sketch the region we did, whose area is given by the integral. We just need to evaluate the integral. I think that's the easier part. Integral of what? R dr d theta. Oh, okay. So that's the integral that we needed to evaluate. Can we do that? How do we do this? Let's integrate the inside one first. R dr should give us r square over 2, right? And we evaluate it from 0 to 2 sine theta. R equals 0 to r equals 2 sine theta d theta. Cool. And so now when we do that, r equals 0 to r equals 2 sine theta, and evaluate it, it just simplifies to 2 sine square theta d theta. And we know how to integrate sine square theta, right? You write this as 1/2 of 1 minus cosine 2 theta and then integrate it. But you have it 2 times, so that's 1/2. 2 times 1/2 is just 1. So we have a 1 minus cosine 2 theta that you integrate and you get this. Plug and chug. And I was quite patient here. What is sine of 2 pi? Is sine of 0. Sine 0 is 0. Sine pi? Hey, sine pi is also 0. Ha! So this is nothing but pi minus pi halves. That's equal to pi half. So this integral is just pi halves. Yeah, what's the big deal? Right? Check this out. We got an answer for this thing as being pi halves. Does that make sense? It does. Oh man. Well, what is r dr d theta? R dr d theta is just dA, right? Integral of a constant dA is equal to A, right? So when we integrate over a certain region, this quantity r dr d theta, let me repeat that. When we integrate over a certain region governed by these limits, dA, we just get A of the region. Isn't that neat? Let me repeat that. When we integrate over a certain region, just dA, we get A. Integral dA is A. But A of what? A, because we are integrating over a certain region, it is the A of that region. So that means the answer to this integral is nothing but whatever the hell the area of this figure is, this region is. Do we know the area of this region? Of course we can. I mean, we don't need calculus for that. It's a circle of radius, if it's a semicircle with radius 1 unit. Had it been a full circle, pi r square would have been the area of that one, r being 1, so pi would have been the area of a full circle. But since this is half a circle, pi over 2 is its area. And all this integration and all that, it showed us precisely that, right? You might wonder, why did you do this, man? We could have just simply said half a circle with radius of 1. Yeah, but would you have been able to do this if the integral is something more complicated, right? So that's the idea. But these are, see, the thing is, simple problems, when you're starting out with a new concept, is the first thing that you should attempt, because that confirms your intuition or whatever understanding you have about this new topic. Hey, this is right. Let me apply it to a simple case. Well, in this simple case, it worked. Let me apply it to another simple case, maybe. You do that. Yep, it worked there also. Now you build confidence that whatever your model is, it actually does work. And now apply it to something more complicated. Okay? All right. The result is understandable. Simply the radius, and there. That's what I said. Cool, folks? All right. Evaluate the integral by changing to polar coordinates. Y square over x square plus y square dA. Ooh. Now, wow. What a fascinating thing this is. It's actually an integral in Cartesian. But what this is saying is, give it a shot. See if you can change this to polar coordinates and integrate. All right, so let's, where D is the region that lies between, oh, they're also giving this piece of information. Yeah, they have to, right? What is the region over which you are integrating this? Is apparently the area that lies between x square plus y square equals a square and x square plus y square equals b square, where a is less than b. A is bigger than 0, all positive. So, the region D expressed in terms of r theta is, the region D. Can we take this region and express it in terms of r and theta? That's the key. Okay. As, would you agree? This is nothing but a circle with radius a. Sorry about that. And this is a circle with radius b. Okay, so that means r equals a to r equals b. Now, is it a full circle or a semicircle or a quadrant of a circle? What is it? Oh, it's full circle. Oh, that tells us theta must be 0 to pi, 2 pi rather. Right? Because it's a full circle. I wish I had just drawn the graph of it. 2 circles. Sorry about that. Okay, now here is the bigger one. So we took care of the region and made sure that we can express in terms of that region in terms of r and theta. And the next order of business is, before we go to next order of business, do you remember? What do we replace dA by? R dr d theta, right? R dr d theta. Okay. And what's up with y square over x square plus y square? You cannot have these. You must have all of this part, the integrand, in terms of r and theta. Okay. X square plus y square is nothing but r square. Right? Yeah, we can do that. Y equals r sine theta. Okay, so we'll replace y square with r square sine square theta. As simple as that. So, y square over x square plus y square is, like I said, this, and we can factor out an r square and we get cosine square theta plus sine square theta, which is 1. So this is r square. Wait a minute. So this whole integral is just sine square theta. Isn't that interesting? Right? Look at what looked so complicated now just became sine square theta. Boy, integrating this using Cartesian would have been much more painful. Okay, so this is equal to this, and oh, especially the region, right? And what would have, okay, all right. So 0 to 2 pi of d theta, theta equals 0 to theta equals 2 pi, and a to b sine square theta, r dr d theta. Well, so that means we will, wait a minute. I think I did this. I first integrated with the inner variable, inside variable, which is r. So dr, with respect to r, I did that. And the limits are constant limits, r equals a to r equals b. And got this and integrated with respect to theta, 0 to 2 pi. B and a are constant, so b is going to go over 2. I can yank this out. And sine square theta, again, like before, 1/2 times 1 minus cosine 2 theta we can write, and then apply all of this. Cool. And so if we've, and integrate this and apply the limits 0 to 2 pi for theta, and we should be done. Okay, so the answer turns out to be b square minus a square times pi over 2. Doing the same thing, figuring this integral out in Cartesian would have been much harder. Okay. There's one more thing that I would like to point out here. Because these limits are constant, a is a constant, b is a constant, 0 is a constant, 2 pi is a constant. Couldn't we have split this into just a function of theta times just a function of r? Yeah, we could have. We could have figured this out by simply saying integral 0 to 2 pi sine square theta d theta times integral a to b r dr. We could have separated it out like that and worked with this one, and that would have given us the same answer as this. Cool? All right. Evaluate the integral by changing to polar coordinates, and where D is the region in the first quadrant that lies between the circles x squared plus y squared equals 4 and x squared plus y squared equals 2x. See, these are the ones that tend to pose a problem, figuring out what the region is when you're given equations like this. D is the region in the first quadrant. Okay. That lies between the circles. Oh, apparently both of them are circles. Let's see. Yeah, x squared plus y squared equals 4. That's a circle with the 0, 0 as center and radius 2. Yep, that's a full circle but then only the first quadrant. So don't pick the whole circle, just pick the quadrant, 1/4 of a quarter of the circle, especially the quarter of the circle that lies in the first quadrant. So that takes care of what this looks like. That's the outside. And the inside one is, apparently this is also a circle. Oh, really? Yeah, it is. Because we can say x squared minus 2x plus y squared is equal to 0. And then we complete the square, and that will give us x minus 1 the quantity square plus y square equals 1. What is that? Let me repeat. If you complete the square, you get x minus 1 the quantity square plus y square equals 1. X minus 1 the quantity square. Oh, that's in the form of x minus h the quantity square plus y minus k the quantity square equals r square. So h is 1, k is 0. So 1, 0 is where the center is located, and it has a radius of 1. So that's what prompts me to draw this picture. The outside circle is x squared plus y squared equals 4 is nothing but center is located at 0, 0, and it's a quarter of a circle with radius 2. That's what we are seeing here. And the other one, the inside one, is this. So the region happens to be between these two things. Ooh, that's a complicated thing to define. If you were to do this in Cartesian coordinates, yikes. Is it doable? Yeah, it is doable, but I think it would be a pain. Yeah, it would be a pain. All right. So let's look at this then. In r theta, express d in terms of r theta is itself. Okay. And outer quadrant is this. R equals 0, r equals 2. And theta, okay. Yeah. Whoa. Outer quadrant. Yeah, let's talk about that outer quadrant. That is something. Wait a minute. I need to mention this. Come on. Sorry about this, guys. So the way we need to look at the D is, that region is nothing but the quadrant of this outer circle minus this semicircle. That's the way to look at it. And now, do you remember I said in the properties of integrals, integral over d is equal to integral over d1 plus integral over d2, where d is d1 union d2. Here we don't do a union, we need to take away, so we actually subtract, right? And so we have the outer one minus the inner one is the concept here. So outer quadrant itself, let's figure out how to represent the outer quadrant in terms of r and theta. And that seems to be fairly straightforward, right? R equals 0 to r equals 2. And theta goes from 0 to pi halves. That part is straightforward. Now the question becomes, how do we write this semicircle in terms of r and theta? Okay, now x squared plus y squared is equal to 2x. X squared plus y squared is nothing but r squared, and 2x can be replaced by r cosine theta. So we have 2r cosine theta. So r equals 2 cosine theta is this curved part. That semicircle is nothing but r equals 2 cosine theta. Well, in light of what we did earlier, we had r equals 2 sine theta, and we picked pi half to pi, and that turned out to be a semicircle that looked like this, right? So now r equals 2 cosine theta stands to reason that it would look like this. Cool. And now where is theta going from? Well, theta is clearly going from 0 to pi halves here for the inner circle. So once we know that, we can split this into two separate integrals and subtract the inside integral from the outside integral over the outer region minus the integral over the inner region. That's how we figure this out. Cool. And x we can replace by r cosine theta, x dA. So x is being replaced by r cosine theta. dA is being replaced by r dr d theta as before. And the limits on r, this is all for the outer region, as r equals 0 to r equals 2, theta equals 0 to theta equals pi halves. And the r cosine theta, r dr d theta for the inside part, which we are subtracting, is the same. The only thing is r goes from r equals 0 to r equals 2 cosine theta. R equals 0 to r equals 2 cosine theta and 0 to pi half. All right. So the rest of it is the straightforward part. Oh, again, we could have separated this out. Cosine theta d theta separately and r squared dr, integrate them and apply the limits and multiply. We could have done that. And it turns out to be all of this is 8/3 minus pi half. Why do we need to learn all of this? Pretty soon, when you guys do fluid mechanics and stuff like that, what if you want to figure out the volume of a fluid flowing through a region like this? You will make calculations like that. What if you had somebody put a sphere inside a pipe, a quadrant of a pipe. The sphere is blocking this part, and the water is now having to squeeze itself through this area and come out. And you want to know what the flow rate is. Well, you will have to do these kinds of integrals. Okay? That's it, folks.